Last time you found out the relationship between the basis change and the vector component change, but you still don't know how the normal component changes. A normal is related to a vector. Let's start with a vector v. You know the relationship, which is a normal function nv equals d. You often see the normal like this. But you already know it is a stack of lines. You can think that d is equal to 0 cases. You can also write the normal equation in the matrix form. This is same as a dot product, and this equals 0. As you see, n is a linear function. Now let's back to the vector v. Let's write the v as a linear combination of the basis vectors. Using these basis vectors, the vector v can be represented as a linear combination of them. You can write v in a column vector like this. You can decompose this vector into two vectors. Then you can take out each component. Since 1, 0 is E1 and 0, 1 is E2, v becomes like this. By the way, you follow a specific notation about subscript and superscript. You write ei, I is in subscript. If the components change follows f, you use subscript. You write vi, I is in superscript. If the component change follows b, you use superscript. So let's rewrite the vi. Depending on which matrix it follows, subscript and superscript change. Now you think about normal. This is a normal equation in general. Let's think that the d is equal to 0 case. The matrix form is like this. In this particular example, v is 2 and negative 1. Calculate the multiplication. One solution for n1 and n2 are 1 and 2. So you can write that n is 1 and 2 as a row vector. In computer graphics, we usually draw this normal as an arrow. We pretend it is a column vector. This is quite intuitive unless you transform it. But the normal is not a vector like v. Normal n is a function that gets v and returns a scalar value. Visualizing a function as an arrow is fine, but you feel a bit odd. You know it is better to visualize it as a stack of lines. You can also represent the normal as a linear combination of bases, starting with n as a row vector. Let's decompose this as n1, 0 plus 0 and 2, and put the coefficients out. Now you can think of the bases epsilon1 and epsilon2 like this. Finally, you write the n as n1 epsilon1 plus n2 epsilon2. These epsilon1 and epsilon2 are the bases of the normal. But what matrix do those follow under the basis change? Luckily, you know how to evaluate the normal basis function with the vector basis. Here is epsilon1, which is 1, 0. Epsilon2, which is 0, 1. Basis E1 is 1, 0. Basis E2 is 0, 1. Let's calculate them. This one is 1 times 1 plus 0 times 0. Others are similar. All of those have a 0. These two terms are 1 times 1. If you calculate them, they are 1, 0, 0, 1. This looks complicated, but it is called Kronecker delta. If the subscript is the same, it is 1, otherwise 0. These epsilons behave like a kind of basis. It's a function which takes a vector and gives us a scalar, but looks like a basis. For a standard basis, there is the basis vector E1 and the corresponding basis normal epsilon1. the basis vector e2 and the corresponding basis normal epsilon2. When the basis changes from ei to ei dash, how the basis normal changes epsilon I to epsilon I dash. This is the theme of this video. For the standard basis, the basis e1 is perpendicular to epsilon 1 and the basis e2 is perpendicular to epsilon 2. When the basis changes, your first guess of epsilon 1 dash is like this. The epsilon 1 dash lines are perpendicular to the e1 dash vector. Then epsilon 2 dash is like this. This is perpendicular to the e2 dash vector. Why do you guess they are perpendicular? One reason is that the standard basis vector ei and standard basis normal are perpendicular. The other reason is that the name is normal. The name normal always sounds like something should be perpendicular to something else. This definition might work because you can represent any vector with a linear combination of the basis vectors. You may represent any normal function as a linear combination of these basis normals like basis vectors. But do they work well? What does it mean that they work well here? Let's say that work well means they work like a basis. Let's think about a vector v, which is equal to e1. This v is parallel to e1, thus there is no e2 component. For a vector which is parallel to one of the basis vectors, there is no other basis component. This is actually the point to think about the basis. You don't need to think the other components. The basis normal function epsilon 1 is this. The first component of epsilon 1 is 1, since the e1 crosses to the line once. But e2 doesn't cross the line, so the second component of epsilon 1 is 0. For epsilon 2, e1 doesn't cross lines, but e2 crosses the line. Thus, the epsilon 2 components are 0 and 1. Each basis vector and each basis normal don't interfere. You want it to the basis in this way. Here, no interference means that the Kronecker delta function holds. Thus, the basis becomes a basis-like thing if it has the Kronecker delta's condition. When you think a basis change like this, the components of e1 dash are 1, 0. But the component of e2 dash are 0, 1. Please note, the first component is not 1. This is because the basis defines the coordinates. If we represent the e2 dash components with the standard basis ei, then it is 1, 1. But the current basis is ei dash. e2 dash has only the second component. That is the reason that the column vectors here have the small ei dash. Let's think about the basis normals components. In your first guess, the epsilon 1 dash is perpendicular to the e1 dash. This epsilon 1 dash has the first component, which is fine, but e2 dash shows epsilon 1 dash has a second component too, since e2 dash crosses the lines. The second basis normal will be like this. This is perpendicular to e2 dash. If we make the e1 dash twice, then it crosses the lines. Thus, the component is 0.5. The second component is 1. However, these epsilons don't make the problem simpler. Especially, the Kronecker delta function doesn't hold. So, this basis normal does not behave like a basis. There is something wrong. You assume that the word normal is always perpendicular to something. Are you deceived by the impression of a word normal? This basis doesn't make the problem simpler. So, your first guess about basis normal seems wrong. Then, What makes the basis normal function a basis? You look back at the standard basis and where the independence comes from. You see that it comes from the epsilon 1 E2 is equal to 0 and epsilon 2 E1 is equal to 0 cases. This 0 gives you independence. This 0 makes something like a basis. This is because 0 means not related. If there's no relation, you don't need to think about that. That is great. You finally see why mathematicians define the basis with the Kronecker delta function. By this definition, you don't need to think about something. You can be lazy. This is amazing 0. The diligent people just work. The lazy people persist in trying to be lazy and make the computer work for them. Therefore, all progress depends on the lazy people. That's one of the reasons you like to learn math, physics, and computer science. The world is so complex, you need to localize and simplify the ideas. To be lazy, you work hard. It is also important that epsilon 1 E1 is non-zero and epsilon 2 E2 is non-zero. You don't care the value itself. Just non-zero is important. The mathematician's choice is 1. I see it is simple, but you think that the non-zero is important to behave like a basis. The mathematicians define the basis by Kronecker's delta, regardless of the choice of basis. Sometimes math notation is too subtle. Only the difference is dashes here. This definition makes each basis independent. A math textbook starts with this definition. However, this is almost at the end in your math journey. You made mistakes. You even didn't know what you wanted. Then you found this, finally. Now you see this definition is natural, straightforward, and inevitable. This is what makes a basis a basis. When the basis changes, how is the normal transformed? The epsilon 1 dash becomes like this. The epsilon 1 dash lines are not perpendicular to the E1 dash. Those lines are parallel to the E2 dash. E2 dash has 0 epsilon 1 components. This means epsilon 1 dash E2 dash is equal to 0. The epsilon 2 dash is like this. Again, the epsilon 2 dash lines are not perpendicular to the E2 dash. These lines are parallel to the E1 dash. E1 dash has 0 epsilon 2 components. This means epsilon 2 dash E1 dash is equal to 0. For the sake of simplicity, you define the width of the magnitude of epsilon 1 dash function to 1. You also define the magnitude of the epsilon 2 dash to 1. Therefore, the normal transform should hold the Kronecker delta. That's how you transform the normal. Actually, Kronecker delta condition and linearity can derive the normal transform. So let's review the linearity first. 1. Additivity. For a vector, you can add vectors first, or you can add them after multiplying the scalar value c. A normal is the same. You can first evaluate the vector and then add, or first add the normal and then evaluate the vector. Both are equal. 2. Homogeneity. For vectors, you can multiply later or first. For normals as well, you can change the order of multiplication. First, a basis vector change uses the forward matrix F. The new basis EI dash is a linear combination of the old basis EI. You already explained why this is 2-1 instead of 1-2. Second, the relationship between the basis vector and the basis normal is the Kronecker delta function. Third, the basis normal changes, but you only assume it is a linear combination of the old basis normal. Your normal transformation matrix is Q. So what is Q? What you want to know is the epsilon I dash ej dash. Say I is equal to 1 and j is equal to 1. This is epsilon 1 dash. And this is e1 dash. Distribute the basis vector and distribute again. Using linearity, you can pull out the coefficients. Use the Kronecker delta condition. These are I is equal to j, so 1. These values are I is not equal to j, so 0. These zeros are a great property of a basis. You don't need to think about it, so the remaining terms are those. The same discussion applies to the rest of the cases. You also know the relationship between the new basis normal and new basis vector, the Kronecker delta. Therefore, these are 1s and these are zeros. Now we know 4 unknowns q and 4 equations, so you can solve for q. However, you are familiar with these highly regular patterns. Here is the patterns. The inner suffix of the first terms here is 1. The inner suffix of the second terms here is 2. The epsilon 1's suffixes are here. The epsilon 2's suffixes are here. The e1's suffixes are here. The e2 dash suffix are here. What is this pattern? This pattern is the matrix multiplication pattern. The multiplication of q and f follows. Let's compare the components. You see that each component of the matrix corresponds with each relationship, and they are Kronecker delta. Therefore, this matrix is the identity matrix. You now know what is Q. Q is the inverse of F, which means Q is B. Finally, you found the normal transformation matrix. That is B, the inverse of F. So far, you think about the normal transformation in the two-dimensional case. Expanding this to the three-dimensional case is not difficult. Actually, you can expand this to the n-dimensional case. A new basis vector can be written as a linear combination of the old basis. The coefficient is the components of the forward matrix F. The basis should have the Kronecker delta relationships. A new basis normal can also be written by a linear combination of the old basis normal. The unknown coefficient is the components of a matrix Q. Let's compute the new basis. Epsilon I dash is here, substitute with sigma qik epsilon k. Ej dash is here, but we need to change the indexes, not to confuse epsilon I dash. Substitute with sigma flj el. Using linearity, we can rearrange the terms. This epsilon k el is Kronecker's delta. Because of Kronecker's delta, when L is not equals to k, the value is 0. We can rename the index L to index k since all L that are not equal to k will be removed. Thus flj becomes fkj. In the same way as before, most of the terms of this summation becomes 0 except k is equal to L. Thus, we can only use k. Then, delta Lk becomes delta Kk, and delta Kk is always 1, so we can remove delta Kk. The left-hand side of this equation is also the Kronecker's delta. We also know this summation is the component of matrix Qf. When the component of a matrix is the Kronecker's delta, it is an identity matrix. Therefore, Qf equals I, then Q is the inverse of F. Finally, Q is B. We found the normal transformation matrix is B in n-dimensional case. Let's summarize the transformation. We have basis vector change and its components change. You started the basis vector change. This transformation matrix is F, the forward matrix. The backward matrix B is from new to old and the inverse of F. You see the vector components use B for the old to new, so the components behave as the inverse of the basis vector change. You see that when the universe expands, the components shrink. You find that the basis normal change is the inverse of the basis vector change, so from old to new, it uses backward matrix B. For new to old, it uses forward matrix F. You find the normal components change uses the inverse matrix of basis normal change. In the notation, when the change followed the forward matrix, you used the subscript. But if the change followed the backward matrix, you use the superscript. It is a standard mathematics convention. The basis normal change followed the backward matrix, thus the basis normal change should use the superscript. You feel a bit happy because you find the simple and symmetric relationships, but you still have 3 remaining questions. 1. Some computer graphics textbooks and Wikipedia say that the normal transformation is the transpose of the inverse of B, not just an inverse. You have already seen that the normal is a column vector in the computer graphics world. Also, you almost always live in the orthonormal standard basis world. In that world with the normal function, you can make a row vector by transposing the vector. Therefore, a transpose is needed. You see that this transpose is artificial. This is broken on a non-orthonormal basis, but many graphic systems use an orthonormal basis. The second question is, why does homogeneous scaling work on just B? The homogeneous scaling matrix is SI. What is the inverse of a SI? It is 1 over SI. In the computer graphics world, a normal vector is normalized. That means the transform matrix is just I. Therefore, normalization makes this work. The part 1 video shows non-homogeneous scaling breaks this. The third question is, why does rotation work on just B? What is the transpose of inverse of a rotation matrix R? A rotation matrix has a special property. The inverse of a rotation matrix R is the transpose of R. Substitute R inverse with the R transpose. The transpose of the transpose of R is just equal to R. Therefore, it isn't actually B, it is the transpose of the inverse of B. But just B looks work. You understand a bit more about normals. Actually, the question of this video could be, what is normal? A normal is a function, not a vector. It is not a column vector. Mathematician calls this a covector. Components of a covector follows the forward matrix F. A normal is also called a pseudovector, since it follows the right-hand rule. Our vector is the pencil model, thus it is physical. However, choosing left or right is a human factor, thus it is not a physical vector like our pencil model. Mathematicians call your vector a contravector because the component of the vector don't follow F, but F inverse. The change contradicts the forwarding matrix. A normal is a covector which follows the inverse matrix of the contravector change. Thank you for coming on this personal journey with me about transforming normals. As you see, I made many mistakes and sometimes don't walk toward the problem. It was not a straightforward way to understand my question. Why is the normal transform the transpose of the inverse? For further exploration, the mathematics of vector spaces and tensor algebra are a great place to start. I will continue to explore more. I basically live in the Euclidean space with the standard basis. In this world, the Pythagorean theorem always worked. Transforming normals and basis changes broke the Pythagorean theorem. The Pythagorean theorem is just a special case. In my old world, I didn't need to care that the vector is a column vector or a row vector. I didn't need a metric tensor since it is always an identity. I don't need dual space, and therefore I didn't understand my university vector space course. On the Wikipedia page, my discoveries in this video are explained in just 4 lines. Now I can see it, but I never understood it before my journey. My journey has helped me. I hope it will help you too. Thanks again. See you in the next video.